Okay, so carrying on with the tangent lines and some other angle properties, got another type of a question here. So line segment AF is tangent to the circle at point E. So that's an important point right here, point E. The line segment DF contains a diameter DB. Another important point there. And angle CFE is 34 degrees. What are the measurements of angle CEF, angle ECF, and angle EDF? Explain your reasoning. Let's go ahead and let's solve for our first one, or let's kind of go ahead and start thinking about this. Angle CEF. Well, I know from the point of tangent C, and since EC is a radius here, that the point of tangent C is going to have to intersect at a 90 degrees. That's one of our laws that we learned about in this unit. So we know this is going to be 90 degrees, and our reasoning here is E is the point of tangency. Point of tangency. And EC is a radius. So just with those two facts, we know that angle CEF is equal to 90 degrees. Perfect. Let's go ahead and let's look at ECF. So ECF, right over here. So this angle here, AECF, it's inside our triangle with E, C, and F. And we already have 90 degrees. We already have 34 degrees. So we should be able to take 180, subtract 90, subtract 34 to equal angle ECF. Reason why we know that, all three of these angles should add up to be 180 degrees. So I'll just do some mental math on the side here. I'm going to take away 124, do a little bit of arithmetic here, 6, 5, 56. And the only reason that we did this is that because it's on the inside of a triangle. That was it. Okay, we can keep on going with this now. And we can get our calculation of angle EDF. EDF. So that's going to be this one right over here. EDF. Now, I think I want to do this question a little differently than we did in the last question. And I want to use a little bit of what we learned in lesson 1. So what I'm going to use here is our arc EB. Our arc EB here. This is subtended by a central angle ECB, which we already know is 56 degrees. I'm just going to put central angle, and it subtends arc EB. Just going to kind of put that as a note. But take a look at this. EDF is actually contained, or it actually contains the inscribed angle EDB. It's kind of interesting. Angle EDF actually is going to be the same as angle EDB. And this is going to be an inscribed angle. Let's spell inscribed right as well. Inscribed angle. And this subtends arc EB. So check it out. We have a central angle that subtends EB, arc EB, and since we know that angle EDF equals angle EDB, it's the same way that we can look at it this way. Then we know that EDB is an inscribed angle that subtends EB. Let's use the relationship between these. So we know the relationship from lesson 1 that EDB, remember that's EDB, is going to be equal to half what angle ECB is going to be, or ECF. Both of them would be the same, multiplied by 56. So if we did it like this, we can just take half of our measurement over here, which is going to be equal to 28 degrees. Okay, so kind of cool that we can get to this just by using this angle. If you wanted to challenge yourself, you could, of course, do something that we did in our previous example, which were to be use the supplementary angle to solve for angle C or ECD. You could solve it that way. And then figure out what these two angles are, since you know this isosceles triangle. So kind of a wild way that you can do it, but you might be starting to see that there's multiple avenues for you to answer these questions. So that's how I do this question, and there is another way to do it.